Okay, let us begin. Let's pick up where we left off. We were talking about linear approximation. It's basically the fact that we can, assuming f is a differential function, and the idea is we can approximate f of x by the equation of its tangent line. So then our f of x will be approximately equal to f of a plus f prime of a times x minus a when x is near a. Also, a is an isomorph. Where you kind of know all the information, you know what f of a and f prime of a are, or we can find easily. And x is at which we want to approximate. So, can have a function, assuming we can differentiate it, this approximation will hold. The closer x is to a, the better the approximation will be. So this allows us to figure out some unknown information if we know some previous information in the past. As well as, not only is that x is near a is important, but also, and we'll talk about this, touch on this today. I think I want to talk about max and min values, but it's also worth mentioning that the slower f is changing, the slower it is increasing or decreasing, the better the approximation will be also. So let's actually do another example. We did one where we approximated the square root of 3.99, and I left another example to approximate. It was the cube root of 8.01. Using the linear approximation. So let's pick up right with that example. Did anyone actually try this? Yeah?
So I started by setting f of x equal to the cube root of x. And
Makes sense. You want to approximate the cube root of something?
and we want f of 8.01. So set a equal to 8 since that's a nicer value. And we know that x has to be 8.01. So that means f of a is going to be equal to the cube root of 8.
So f of a equals the cube root of a, which is the cube root of 8, which is 2.
And f prime of a will be equal to 1 over 3 times the cube root of 8 squared, or 64.
Now, again, remember in general, when our a is positive, we do have the option of either taking the radical first or the power first. In general, it's nicer to take the radical first whenever possible. So we would take the cube root of 8, which is 2. Then I'd square that, which would give me 4. Then I'd multiply that by 3, which would give me 12. So 1 over 12 is what we have here. Yeah, then what?
So now you can use the linear approximation formula, which is L of x equals to f of a plus f prime of a times x minus a.
Plugging these in, we would have 2 plus 1 over 12 times 8.01 minus 8, which is just 0.01, which is 1 over 100. So this is 2 plus 1 over 12 times 1 over 100. That's 2 plus 1 over 12. Now I can write that as a single fraction. So 2 is 2400 over 1200. And then I'm going to add 1, so this is 2401 over 12. What is that approximately? Anyone have a calculator?
2.00833.
2 zeros?
0.3.
And it's one of those that does that? Okay. Yeah. You know what the actual answer is? I mean, an approximation of the actual answer.
2.00832.
What's after the 2?
No idea, but I stopped at 2 because I was like.
Did I do what's after the 2? It is in fact a 9 that comes after the 2. Which means, if I round it, I'm good up to 6 decimal places here. Last time, I believe we were good up to 4. So this kind of goes back to what I was saying at the beginning. The thing is, the cube root function actually changes a lot slower than the square root function. And so the new y value is going to be closer to the old y value. If I were doing this with a function like e to the x, for example, want to approximate e to the some decimal point, your approximation won't be that good because e to the x actually grows really fast. We know that exponentials grow really fast. But yeah, for cube root or square root, we can get up to like 6 decimal places with not a lot of work. So, also as I mentioned, you will see something like this on the next quiz, which is going to be next week, as well as the next test. I'm definitely going to ask you to use the linear approximation formula, probably in one part of one question. And so this is something that you should know how to do. It's just for illustrative purposes. But you know, there are bigger problems that you can use this to solve other than computing something that you could actually punch in your calculator. It's just that at this level, it's kind of hard to come up with a useful example that you'd appreciate and you'd actually be able to calculate with only Calc 1 knowledge. But yeah, this is linear approximation. We can use a tangent line to approximate what's going on with a function. And you can actually get pretty good just by hand. There is another flavor of linear approximation, which was also in the title, called differentials. And that's basically when we want to focus on the change. It's the same idea as linear approximation, actually. Different focus. Same way how the average rate of change formula is the same as the difference quotient formula, except when we think average rate of change, we think of the formula in a particular way. Same thing we can do with quote-unquote differentials. The differential is the guy that looks like the dy or the dx. That's what we call them, differentials. And they're an important concept. You can actually build up a whole theory of math just focusing on differentials. But for us, I just want us to appreciate that if y equals f of x is a differentiable function, is given by dy equals prime of x. X, basically what I did here is just I differentiated, found dy dx, you get f prime of x, and then I multiplied both sides by dx to get something that looks like this. This part here, this is called the differential of y. By the way, this guy is called the differential of x. Now, when x is your independent variable, your dx is actually equal to the delta x, since x is the independent variable. So remember that delta x, the uppercase delta x, is just a measure for the change in x, which is the specific exact change in x, the non-approximated form. However, because x is the input, we are controlling that. I know exactly how much I'm going to move the x. And what I want to do is see how the y is going to respond. So the differential of y, usually you want to think of that as just an approximation of the actual change in y. So the actual change in y, I might not know. I know what change in x, I know how I'm manipulating the inputs, but I want to know how does the output actually respond to this input. And sometimes actually computing how much the output actually responds is difficult. So what we can do is we can approximate it using a differential. In other words, we are using the slope of the tangent line to approximate the change in y. And what you can also notice that how we can think of this. What you can do is think of as x is changing. You can talk about the new y value in terms of the old y value plus the change in y. And that's how you can kind of think about it. And now if you really actually flush out what that means, well, the old y value is simply just the function evaluated at a point. I knew the old point being x equals a, and this part is just going to be the derivative times dx, which is this guy. But I know that the dx is actually the same as delta x, so it's actually going to be x minus a. It's the difference in the x values. So this is actually exactly the same as linear approximation. It's just a different angle of looking at it. When we want to focus on the change and not necessarily the new y value, we use the differential. This is called the differential. It's a very useful function. Let me give you an example of where we can use it. And again, this is just for illustrative purposes. This kind of problem is something that you can solve without calculus, but I just want to solve it with calculus to show you that it's actually does work. A problem like this could also show up on the test. I'm definitely going to ask you to approximate some number, some value, but there might also be something like this, a word problem, where we want to use differentials. So. actually the opposite, but whatever, it's going to still work. Suppose we have a right circular cylinder. The height is 20 centimeters and the radius is 10. Here's the thing though, but there is a possible error in these measurements. So you have something that you're measuring its dimensions, but the instrument that you're using to measure it isn't completely accurate. You know for a fact that that instrument does have a possible error that can occur. So let's suppose the possible errors in these measurements. Let's say we can be off by 0.1 centimeters. Okay? So we have something where the height is 20, but I use an instrument to measure it that doesn't do it perfectly. So the height could in fact be as high as 20.01, or it could be as low as 19.99, right? So I'm a little bit off, okay? So assuming the error in these measurements can be as large as that, right? So now, here's the question, A. What is the maximum possible error in finding the volume of the cylinder? B. What is the relative error? So we're going to do this. So a very simple Calc 1 version of a problem, which again, you don't actually need calculus to do this here, but I just want to show you that calculus is another way. There are situations where you would need calculus. Some possibilities that come to mind is something like this might show up in engineering. Sometimes you're in engineering, when you want to build a bridge across, and I don't know if you guys have ever watched documentaries on building bridges, but the longer the bridge is, it gets a lot harder to actually do the calculations and the measurements and all that good stuff. You're building a bridge that's going to be 5 miles long, right? If you're off by 1 meter, that could be a problem, right? So sometimes we know that, okay, we're doing this thing, we're gonna make a mistake somewhere. Then we're just gonna judge, okay, how wrong could we possibly be, right? And there are techniques to think about, okay, in measuring a 5 mile long bridge, we're gonna be usually off by this much. And then we want to actually quantify this error. And in certain cases, like the ones with bridges, if you are outside of the error by too much, it can literally cause a loss of life, right? So it's very important that you fully understand the errors that you can actually make. So if I know that concrete is supposed to weigh this much and it's supposed to be this strong, and if I stretch it out this much, it's supposed to be able to support this much weight. If I'm building a 5 mile long bridge, do we have enough concrete? Right? What are the calculations that are going to go into that, right? So when we start doing things and molding the concrete, how is the error that we started with going to be going through all these processes, right? So we have a cylinder, we know that the dimensions aren't perfectly measured, which automatically means if we're going to measure the volume, we are also going to be off in the volume. So now we want to know that, given that we know the error or the maximum error in the individual measurements, how does that error affect us calculating the volume, right? Which is it's a problem that arises all the time. Sometimes we kind of know we can't be perfect in one situation, but we want to know if we compound that situation, how bad can things actually get when we use our errors to do other things. One way you can tackle such a problem is with differentials. So here's the idea. We can think of the error in volume. Let's call volume V as a change in the volume. Namely, I'm going to measure dV. dV is going to tell me how big the error is, right? What is the change in volume that results in me moving from, say, 20 centimeters to 20.01 centimeters? What is that error going to be? So what we'll do now, we'll start with a function that measures the thing that I care about, namely volume. So we are going to have volume equals pi r squared h. Know that that would be the volume of the right circular cylinder. Okay. So we have a right circular cylinder here, but we could be off. It could actually be slightly bigger than this, what we imagine. It could also be slightly smaller than what we imagine. So there is a change in the volume that I care about. What is this potential difference in volume over here? Right? That's kind of what I want. How much can we be off in measuring the volume? Well, I know this is the formula for volume. I want to measure what is the change in volume that results if I change my R by this much and I change my H by that much. Now this next part might be a little bit confusing, but I'll explain it after I write it down. Here's how dV is going to work. So we know what the differential is. I'm just going to want to take the derivative of this and multiply by the differentials of the individual variables. However, again, just like with related rates, what you want to notice is that we actually have two functions here. There's the radius that's doing its thing, and then there's also the height that's doing its thing, which means there should be some sort of product rule happening here. And that is in fact what I'm going to do. So I'm going to differentiate one at a time. I'm going to differentiate the R, leave the H, then differentiate the H, leave the R. And here is how things are going to look. So I have 2 pi r h, and I'm going to multiply by dr, which is going to be the change in r, plus I'm going to leave the r, differentiate h, which is 1, and I'm going to multiply by dh. So that will be the equation that defines the differential. Now, it might look a little bit weird, and when you get to Calc 3, that's not going to be weird at all. You're going to learn something called the multivariable chain rule, and that's going to be just automatic. But in the Calc 1 sense, why would that be the way things look? You can probably think of it in this way. You can think of this as me just going through and differentiating with respect to some other variable, say t. And that, we know how that would look from related rates. So we would get dv dt is going to be equal to 2 pi r h dr dt plus pi r squared dh dt. And the thing is, with the Leibniz notation, you can actually treat the differential notation as a fraction. Then multiply through by a dt. What's going to happen is all your dt's are going to cancel, and I would get the equation that looks like that. So I can go from a situation where I'm talking about the rates, the rate of change of R, to actually talking about the actual change in R, the approximation for delta R. But of course, you don't have to write this down, you just write that down. Whenever you know you're doing differentials, kind of treat it like related rates, except you don't need the dt part. We just care about the top parts. Now, all we have to do is just plug in our values. Suppose R we saw was 10, H is 20. The possible error, the change in R could be 0.01. The change in H could be 0.01. Which means the change in volume is going to be 2 pi times 10 times 20 times 0.01 plus pi times 10 squared times 0.01. So this is 200 times 0.01, pretty much the tens kill the decimal part, and we have 4 pi here. And this is 100 times 0.01, so that kills the decimal part, and we just have 1. So this means the change in volume is going to be 5 pi centimeters cubed. This is the max error in computing the volume. So, in this hypothetical situation, if we had a cylinder whose height was 20 and the radius was 10, and I know I'm measuring these things with an instrument that could be wrong by as much as 0.01 centimeters, then it means that the volume that I calculate could be off by as much as 5 pi cubic centimeters. So that'll be 7 centimeters cubed, roughly. Yeah.
So if it were to be minimum error, you would just not flip it, but make it negative. Like instead of max error in computing volume, it'd be like if you were to ask minimum error.
Yeah. This actually works for both. What you'll realize if you had minimum error, all that would change here is that these two would be negative. And so you get a minus this. So you can think of this automatically as implying a plus or minus. It's implied. You don't really need to worry about the sign. So you know we'll be off by that much. We'll either be over by that much or under by that much. So this is implied. So when we say we could have this much error, you might also want to add, oh, that's an overestimation or an underestimation. But yeah, both will actually work because you'll just change the DRs to negatives as opposed to positive. You just get the negative of the entire thing. What do you think the relative error would be? When we say relative error, what does that mean? Well, relative to what? This basically means the error as a percentage of what the assumed volume is. I.e., your relative error here is going to be the possible change in volume over the volume itself. How much of the volume does this number represent? So that is going to be 5 pi divided by it's pi times r squared times h. This is 4 times pi, so this is 1 over 400. And what is that? That's about 1/4%, right? So that's not true. So going back to that engineering example, what you would normally have is you normally have guidelines, right? So you are going to somehow try to approximate how wrong you could be in measuring the dimensions that you need to build this bridge. However, there will also be a guideline that says, hey, if you're wrong by this much percentage, that's bad. You need to do something else, right? So your calculations aren't good enough. There'll be a threshold. And they'll say, if you're wrong by this much, it's kind of fine, don't worry about it. Especially in engineering though, what they tend to do is they tend to over-engineer something, and they tend to actually go beyond what is actually required of them, which I guess is good. So a lot of those times when you see an elevator, like, oh, you can't have more than 200 pounds in this elevator. Really, it's like, we feel like it can hold 350 pounds, but we're gonna put 200 pounds just to be safe. Right? Because just in case we're wrong by a certain percentage, and then some. Right? So that's just some applications here. I mean, it's kind of a silly example. You could actually figure this out without calculus, but using calculus to demonstrate this kind of thinking is something that you'll need to know about for the future. In cases where it's very hard to work it out by hand. Any questions on this or the previous example? Because this kind of ends what I wanted to talk about, linear approximation and differentials. Yeah?
So you just chose your GH, like you chose the amount of error that they in
Yeah, and that was given in the problem. So they said, we could be off by this much. You're going to pick that as your change. Yeah. Yeah, so for this section, those are the two kinds of problems you want to be able to do. Like I can give you a number, hey, the fifth root of 31.9, approximate this, and you should be able to do that. Versus I could describe something to you, like it's some kind of geometrical shape. Oh, we're measuring a box. The dimensions are 2 feet by 3 feet by 5 feet, but we could be off by 0.1 feet. What is the error in measuring the surface area of the box or something like that? So you can do all these things. Those are the two main kinds of problems that we want to do in this section. And that being said, I want to move on to another topic. I forgot what the section number is for this. I believe it's 3.1, or probably 4.1 in your textbook. Going to be on maximum and minimum values. Very important application of differential derivatives. And we'll be using these applications for a while to do a bunch of things. But first, let's actually talk about what these things are. So here's the thing. There are nice shapes that we know how to find maximums and minimums for very nicely. Probably one of the few examples of this is going to be with quadratics. We know that if you're giving me a quadratic equation, I can find the maximum or the minimum point of that quadratic by finding the vertex. And we have a nice little formula for the vertex, right? X equals minus b over 2a, right? That is going to either give me the xi at the highest point if the coefficient of the x squared term is negative, or it'll give me the value of the lowest point if the coefficient of the x squared term is positive. However, what if I didn't have a quadratic? What if I had a cubic? It turns out you don't have such a formula anymore, right? And for general functions, there's no nice, oh, just do this formula and we can find the maximum and minimum point. How do you go about finding maximums and minimums as a general idea? There is no general formula, and we wouldn't want to rely on one anyway because we want to be able to apply this idea to any kind of function that might pop up. It turns out calculus helps us with that. So let's just make some definitions first. Suppose we have a function. Let's talk about the kinds of maximums and minimums that we would care about. We say f has a global maximum or absolute maximum at x equals c if the following holds. If f of c is greater than or equal to f of x for all x in the domain. This is called a global maximum. What is the largest y value on the entire domain of the function? The entire domain that we're considering anyway. I want to find the y value that's larger than, essentially equal to, every other y value in the entire domain. Similarly, f has an absolute min of global min at x equals c if f of c is less than or equal to f of x for all x in D. These are called the absolute or global maximums and minimums. I'll describe what these are to you in pictures pretty soon. There's another kind of maximum and minimum I care about. There's something called a relative maximum. There's that vague language again. It just means that when you're near the point C, this y value is going to be the highest point in that local region. Probably not in general, but if we were to zoom in on that point really, really close, the y value at f of c is going to be larger, similarly. These are called the absolute and local maximum and minimums. Here's another vocabulary phrase that you're going to want to know. Vocabulary is important. A general term. For maximums and minimums is extreme points. And the plural extreme points is called extrema. So if I were to ask you, find the absolute extrema of the function, what I'm asking you to find is find all absolute maximums and minimums of the function. It means the same thing, right? So extrema is just a general phrase that means either a max or a min. So it'll be a word that you'll see very commonly used in this context. Find the absolute extrema. Find the local extrema. They're talking about finding the maximum and minimum points. I think now I want some examples so you can kind of see what I'm talking about here. I'll wait till you guys copy down those definitions. Then I'll draw some pictures. A picture is worth 1,000 words. Being able to write something down in words or mathematically as an equation is very important, though. Which still a few people struggle with on the test. When I asked them to define what does it mean to be continuous, still have people writing things down like, well, it means you can draw it without lifting your pencil off a page. Which is true, but it's not helpful. It's not a helpful definition. That's not something you can mathematically check easily. And people who tended to define things that way, when we went to the next part of the question, we actually asked them, okay, find A and B that makes this thing continuous. They had trouble with that because they didn't know what equation to check. A lot of people had trouble with that, by the way. That was probably one of the questions that most people had issues with, I think. That and surprisingly, the derivatives problem. People are usually good at the derivatives part. It's the word problems is what they don't get. But a lot of people didn't know the derivatives. Okay, that's good. So this is the definition. Let's make sure that we can identify this with pictures. So we're going to talk about the extrema of f of x on, let's say, an interval a, b. Here's one scenario. It's A, it's B. Another scenario. It's B. Another scenario. Another scenario. go through and identify some points. AM, this means absolute max. LM, local max. And lowercase AM, absolute min. Lowercase am and lowercase lm. I want to go through these graphs and identify all of those features. First one, do we have any absolute minimums? On the interval AB. Are there any y values for which, let me actually make these clear. This is shaded here. This is shaded here. This is shaded here. This is shaded. Also want this shaded. Shaded. This is also shaded. This goes down forever. This is shaded. This is shaded. That's not shaded. Okay, absolute mins. Huh? Yes, no? Maybe so?
No.
What's the definition of absolute minimum? So it's a point where the y value is going to be smaller than every other y value on the function on the interval of consideration. On the interval AB, are there any smallest y values? 0 is the smallest y value. It occurs here and here. There is an absolute minimum at A and B. By the way, these are also, just by definition, also local minimums. Also local minimums. But usually, absolute would precede local, supersede local. We care about that more than we care about these. So it's automatically the case once something is an absolute minimum or an absolute max, it's automatically a local minimum or a local max, but the other way is not true. Any absolute maximums? Yeah, the very top, right? There is an absolute maximum here. By the way, it's also a local maximum. Won't always say this. It's implied. So if something is an absolute extrema, it's automatically a local extrema. If he's the biggest or the smallest guy on the entire domain, then for sure he's going to be the biggest or the smallest guy when you zoom in. So that'll go without saying. Anyone else? Well, no. What about this one over here? Absolute minimums? Yeah.
At point A, absolute minimum and local minimum. And at point B is absolute max and local max.
Yep. Yeah.
At point A, there's an absolute minimum. And there's no absolute max.
So no absolute max. Is there a local max? No local max either. What about this one? No extreme. No minimum, no maximum. How do we you know, if you were to pick any point, boom. Is that the highest point? No, there are points higher. Is that the lowest point? No, there are points lower. Right? What if I zoom in? Still the same idea. No matter what point you pick along here, there'll be points that are higher and points that are lower. This has no extreme, points. This one has a bunch, so intuitively you kind of know that you want to focus on like the top of the hills and the valleys, the depths of the valleys. So you kind of intuitively feel that these guys are going to be some sort of maximum. What kind of maximum is this?
Local max.
Local.
Absolute max.
An absolute max. This?
Local minimum.
So this is local minimum. This?
Absolute max.
Absolute minimum. Anywhere else are we good?
Local maximum at point B.
There's a local max at point B. How do I know? Well, if I were to zoom in, that point is going to be the highest point in that region. I know that there are higher points elsewhere, but I don't really care. If I zoom in locally, that's the biggest Y value. Any other situations?
A local minimum.
A has a local minimum. If I were to zoom in, that's the smallest Y value in that region. This. So, kind of already feel that this is going to be something, and that's going to be something. I also have some points here. Let's call this point A, call that point B, call this point C. Okay. The green dot.
Local maximum.
So local maximum. Pink. So local minimum. C. So local minimum. Why not absolute minimum? Because this thing keeps going down. There will be negative Y values. Okay. Absolute maximum. What is this?
Local maximum.
It's not a local maximum.
Wait, no. Which one here would be?
How do you know? If you zoom in to point B, what are you going to see, right? So we kind of put on like blinders where we only look a little bit to the left and a little bit to the right of that thing. Okay? Is that point the highest point in that strip?
No.
No, there are points up here. Is it the lowest point in that strip? No, there are points down here. That's nothing, right? So that's a fake. It's nothing. You ain't nothing. That's nothing. B is nothing, right? It's not the highest point in this region. It's not the lowest point in this region. Is there an absolute max here? No. The absolute max would be here, but that point is not within the domain of the function. We are always increasing to that point, but we'll never actually get there. So there's no absolute maximum. And because this graph keeps going down, there's no absolute minimum. So it's very important you realize when you're doing with local, you zoom in and you just make sure either a little bit to the left or a little bit to the right is he the biggest or the smallest guy. Whereas with the absolute max, when you zoom out and you look at the thing as a whole, is there a bigger or smallest guy? And of course, you have to be able to actually exist at the point in order to make this designation. So I think most of us intuitively know about the tops of hills and the depths of valleys, but you can have functions that have strange behaviors like this where you really have to pay attention and be very careful. So based on our definitions, that's how we'd identify absolute maximums and minimums and local maximums and minimums. Any questions on? Now here is something cool, in the sense that it's something you can know in general. Now there are many people who use this as an axiom, meaning they just think of it as something that they don't need to prove. It's so blindingly obvious. Other people would start at something else and prove it, but to start at that other thing is probably outside the scope of calculus 1. So we will be calling this thing a theorem, but it's more or less for us going to be an axiom. It's something that it just makes sense for that to be the case. It is called, it's a very important theorem though, it's called the extreme value theorem. First, it'll be an axiom. An axiom is just some mathematical fact that we take true on faith and don't prove it. We just say that has to be true. Okay, here's what the extreme value theorem says. If f of x is a continuous function, what does it mean to be a continuous function? What does it mean to be continuous?
F of A, if you want the definition of it,
Yes.
f of A is equal to like the limit, I suppose, say, of x.
Right, that is what it means to be continuous at a point. So continuous in general means that that equation holds for all points in the domain. So they say, what is a continuous function? It's a function that's continuous at all points in its domain. What does it mean to be continuous at a point? The limit as x approaches that a is equal to, of f of x is equal to f of a. Now, suppose we have a continuous function on a closed interval. Then, f is guaranteed to attain absolute extrema on a, and I'm talking about both of them, the max and the min. Now you might have recalled from the examples that I just erased, there were situations where we didn't have absolute maximums and minimums. And I would also have you realize that in all those situations, I drew an example of a function that was not continuous. Once your function is continuous on the entire interval, there has to be an absolute max, there has to be an absolute min. Right? Because the moment you don't have that, well, it either means you have a hole, like what happened over here, or it means you kind of increase forever, which means along this line you have no definition, right? So you cannot not have an absolute max or min if you have continuity. Once you're continuous on the entire interval, you will have an absolute max or min on that interval. So that's another very basic but very important property of continuous functions. If your function is continuous, you are guaranteed to be able to find an absolute max or min. It's called extreme value theorem. Let's talk about another thing that is also super important. We want to try to start to segue into how do we actually locate these points. So it's one thing to know that something's going to have a max or a min, whether absolute or local. It's another thing to actually find the location at that point. Like I said, if we're looking at a quadratic, x equals minus b over 2a. We know that. What if we're looking at something else? So that's the name of the theorem. You should just know the statement. Now, suppose in addition to continuity, f is differential on the integral. Now here's something else that I'm going to tell you. And suppose f has a maximum or minimum at x equals c. So there is some function that we know is both continuous and differentiable on AB. So A and B have filled in points at the endpoints, and the function is moving in a nice way in the middle. Now, suppose I identify one point where I know there's a max or min, call it at x equals c. What can we know about the behavior of f at that point? It turns out that if you can find the derivative and you know there's a maximum or a minimum, the derivative will attain a very specific value. What is that value? Let's actually figure this out. Suppose f has a maximum at x equals c, then what this means is that f of c is going to be greater than or equal to f of x for all x near c. Now, to be very suggestive, I'm going to write this sort of thing. I'm going to write x in a certain way. If x is near c, we can write x is equal to c plus h, where h is small. Right? So if you're close to c, it means that you're c plus or minus a little bit, in other words, is what I'm saying. Right? Take c, you add a little bit or subtract a little bit, that gives you the point x, which is super close. H is a very small number. Now, what does that mean? This means that f of c is going to be greater than or equal to f of c plus h. In other words, if I bring this all to one side, let's subtract f of c from both sides to get 0 over there. I would have f of c plus h minus f of c. Now we have two cases here. Suppose x is to a little bit to the right side of c, meaning that h is positive. So I take c and I add a little bit. That means h is positive. X is on the right side of c. Or h is negative, meaning x is on the left side of c. What would that actually imply? In case 1, here's what will happen if I assume it's to the right side. So if I look at points on the right side, all points close to it on the right side, this is what's going to happen. This means that if I were to take f of c plus h minus f of c, and let's say I were to divide both sides by h, it turns out because I'm dividing an inequality by a positive number, the inequality sign is going to remain in the same direction. So this means that f of c plus h minus f of c all over h is going to be less than or equal to 0. Now what I'm going to do is I'm going to let x inch closer and closer to c. So I can take the limit as h approaches 0 on both sides. What is this? The derivative evaluated at c. F prime of c must be less than or equal to 0. Now suppose I'm looking on the other side. Suppose I'm looking at points that are to the left of the maximum. What that would mean is if I take this inequality and divide by h, what's going to happen? Well, the sign turns around. Right? That's how inequalities work. You multiply or divide by a negative, the sign is going to flip. Again, I am going to 0 over h is just 0, and what I'm going to do is I'm going to take the limit of both sides. The limit as h approaches 0 specifically. And what's going to happen is the left side is again f prime of c. And the limit of that side is 0. So we have that. So now I'm in the case where if I'm looking on the right, f is less than or equal to 0. If I'm looking on the left, f is greater than or equal to 0. What can we conclude? F prime of c is greater than or equal to 0, and f prime of c is less than or equal to 0.
And it's equal to 0.
Has to be 0. Why? Squeeze theorem. By the squeeze theorem, a lot of people misuse that on the test also, now that I remember. By the squeeze theorem, we must have f prime of c equals 0. If you are located at a maximum or a minimum and the derivative exists there, the derivative must be 0. That's an important theorem. It is called Fermat's theorem. Not Fermat's last theorem. He had several. That's the guy who tormented mathematicians for like 300 years, 350 years, until Andrew Wiles solved Fermat's last theorem. You guys know about that, right? You know what Fermat's last theorem is? People are literally working on this for hundreds of years. It got solved in, I want to say 1994. But it's been an unsolved problem for 300 years because this guy, some amateur mathematician, scribbled in the margin of one of his books one day that, oh wow, I discovered the most amazing proof. And he wrote down what it was. And then everyone's like, is that true? How did he prove that? He never actually wrote down the proof. He just said he had a proof. But then no one could actually figure out a contradiction to this proof. So we know like, this is not down here. You know like how you have the Pythagoras theorem? Suppose you replace the 2 with something else. Like you're looking at a to the n plus b to the n equals c to the n, where your n is greater than 2. So we know nice numbers that work here, like 3, 4, 5, things like that. Fermat's last theorem says if your n is larger than 2, no integers are going to work. And everyone's like, is that true? Try it. There's an infinite number of choices, but there are no positive integers that will work in that. Fermat's like, yeah, you can't solve that equation with integers once your n is larger than 2. And it took mathematicians 300 years, 350 years to figure that out. A professor from Cambridge in, I think, 94 wrote a proof to it. It took like 1,000 pages, something like that. 1,000, 1,200 pages. Because he had to invent kind of new math in order to be able to talk about it. So, yeah, that's Fermat's last theorem, very important theorem. There's a nice book about that called Fermat's Enigma. It's one of those books that it's written about a math subject, but it's a popular book. Like anyone who can read it can kind of get what it's talking about. It was really fun. It's a fun one. I like it.
So what did he get? The professor at Cambridge in 94, what did he discover?
Well, he proved that that's true. That if
oh, did he get that?
I don't remember if he got a prize. He definitely got the rep. He has the reputation now, right? Everyone knows Andrew Wiles from Cape. Yeah. It was a big, it used to be a big deal. All the kids I talk to these days, no one knows what I'm talking about. But it used to be a very big deal. It's literally for hundreds of years we've been working on this. Okay, Fermat's theorem though, that we have in Calc 1, it's not so hard, I just proved it for you. It says the following. If f of x has a max or min at x equals c, and f prime of c exists, meaning we can actually find the derivative, the function is differentiable, then f prime of c equals 0. This is called Fermat's theorem. If you have a max or minimum and calculus works where you're looking, the derivative has to be 0 at that location. I want you to note a very important thing. The converse is not true. So, especially for those of you who are going to be like math majors or going really far in math, you know, sometimes I seem a little crazy when I'm talking about, oh, you have to pay attention to detail, memorize the whole rule. All the little details are important. It's really because all the details are important. A lot of times in the English language, sometimes we automatically assume that the reverse of a statement is automatically true. In math, you have to be aware that this is not the case. Whenever someone states something in a certain order, it has to be in that order. If they wanted the other order, they would specifically say so. They would use something like an if and only if, for example. Right? So this says, if there is a max and the derivative is there, then the derivative is 0. It is not true that if you know the derivative is 0, it means there's a max. It does not work the other way. So this is to say, if you know if f prime of c equals 0, it does not mean that f has a max, f has an extrema. There's a nice example here. Look at y equals x cubed at the origin. If I look at f prime, that's 3x squared at x equals 0, f prime equals 0. But guess what? You know what x cubed looks like. There's no max or min there. Not an extreme point. Okay? So this statement works in this specific direction only. If you know the derivative is 0, it does not mean you have a max. Okay? It's also worth mentioning that there is a blind spot to the statement as well. Because it talks about f prime existing. What does that mean? If f prime doesn't exist, you won't have a max? Well, no. Because if that was true, the statement would specifically say that. Specifically. That's also not true. Also, note, it is possible to have an extreme point without the derivative existing. Anyone can think of an example? Yeah? Absolute value. We've talked about that guy several times. Look at the absolute value function. At the origin, that is an absolute minimum at the origin. F prime does not exist at the origin. We actually proved that the derivative limit does not exist at the sharp corners. F prime of 0 does not exist. So, just because you can't actually do calculus doesn't mean you don't have a max or min. And just because you can do calculus and you get the derivative of 0 doesn't mean you have a max or a min. But it works the other way. If there's a max or min and you can do calculus, the derivative has to be 0. Now you might wonder, well, that's not very helpful, is it? Because I mean, if I just find where the derivative is 0, I'm not going to know for sure if it's a max or min. And it might be the case that maybe there's a point where I can't find the derivative, and that's the max or min. So Fermat's last theorem isn't really constructive in the sense that it's going to help you solve a problem. What Fermat's theorem tells you about is the points that you want to focus on. While they may or may not give you max or minimums, points where the derivative is 0 or the derivative does not exist will be important points for you to look at. This leads to another definition, which we will call critical points. It is critical that we find these points. X is called a critical number if f prime of x equals 0 or f prime of x is undefined. This you need to know. These are the points that we have to pay attention to. If you're looking for maximums and minimums especially, you are going to want to know for your function, where's the derivative not defined, where's the derivative 0? Because these guys will be the prime candidates for finding the maximums or minimums. In the above, the point x comma f of x is called a critical point. Public service announcement. It's very common for someone to use the phrase critical point to refer to the x value. Technically it's not incorrect, but it's kind of okay. We kind of know what you mean when you say it. So someone said, oh, there's a critical point, x equals 1. We know the point technically is 1 comma something else, but we might just say critical point when we're really talking about the critical number. And that's just tradition, I guess. That's what we would call it. Okay. But the values where the derivative is 0 or undefined, these are very important values for us to know about because they tell us many things about the function, but more importantly, most importantly probably, where maximums and minimums will occur. So now let's talk about how do we find extreme points. one at a time. I'll tell you the method we can use to find them, and I will write down some examples, but we won't do them. We'll actually just end up with this. So let's talk about finding absolute extrema first. There's a method called the closed interval method. So called because it works only on closed intervals. We know from the extreme value theorem that once we have a closed interval and we have a continuous function on that interval, that function will have absolute extrema. So this says suppose f is continuous on AB. Closed interval method says, 1, find the critical points of f on AB. And evaluate them. Y equals f of x. Evaluate their y values. So there might not be critical points, just find any critical points and evaluate their y values. You might say, oh, there are none. 2, you will evaluate f at the endpoints, i.e., you're going to find f of A and f of B. Third, you're going to compare parts 1 and 2. The largest y value, that's going to be your absolute max. The smallest y value, the absolute min. We state these in a certain form. F of C equals D form. So, for example, an answer to a problem could look something like f of 1 equals 7 is an absolute max. F of minus 1 equals 0 is an absolute min. Or you actually could say D here. And that would be your answer. You state it like that. So that's one way you can find absolute max or min. Now, we assume we have a continuous function on a closed interval when doing this, because the extreme value theorem says that's the only time we can guarantee that they'll happen. If we don't have that, we might have it, but we're not guaranteed to find it. But that will always be the situation in the top one. I'm always going to give you a continuous function on a closed interval, and if I ask you why does it have to exist, you can just tell me the extreme value theorem says it has to exist. So how would you go about doing it? Find the critical points, because there are potentials for the maximums and minimums, even though they might not be. Evaluate the function at the endpoints, because as we saw in previous examples, you could have a highest point actually occurring at the endpoint. It's possible that the endpoint is a maximum or a minimum. You're going to compare these two, right? So you find the critical points, find the corresponding y values, evaluate the endpoints, find the corresponding y values. Then along all of those, you look for who's the biggest y value. That's going to be your absolute max. Who's the smallest y value? That's going to be your absolute min. So here's the example. Try it for Wednesday. First example, we're going to do another example on the locals. Find the absolute extrema of the given functions on the given intervals. I only did two, but try them. A, your y equals x to the fourth minus 4x squared for x between minus 1 and 3. B, your y equals 2 sine x minus cosine 2x for x is between 0 and 2 pi. We'll stop there, make sure you try those. So, I'm going to get the test back. The solutions are already on the class webpage. There are a few days now. So what I want you to do is look over your test, tally up the scores, make sure the grade that you got is the grade that you were supposed to get. Make sure you actually understand where your grade comes from, and if there are any discrepancies or issues, you can let me know. One thing I would say is we actually have a lot less time than you might realize left in the semester. So, for anyone who did not do well, I would define not doing well as, I guess, below a 70. So the grade on the test, bonus was allowed, and I did have a couple people getting more than 100 on the test. So what happens in that situation is that the extra points that you got over 100, I'll take that and you can add that to test 2. As far as other people who might have gotten less than 100, so suppose your grade was, say, 75, and what I write is like a circle, and then I put a +4. What that actually means is in the test you got a 75, and then you got 4 points from a bonus. So your actual grade, I'm going to add these together, 79 is going to be your actual grade, right? It's going to be the sum of the bonus points plus the points from the test. Now, if the number in the circle is under 70, you are in trouble, and you need to actually do something differently other than what you've been doing. What I would say, if that number is under 40, you're in major trouble, and you probably want to get a tutor at this point. You probably don't want to study on your own at this point, because you don't really have the time for it. You have a month and change till the final. It's not going to be very efficient to study on your own. So if your circle number is under 40, what you definitely want to do, you kind of want to get a tutor and get personal attention with that tutor. If you're between a 40 and a 70, you can probably escape with going to the tutoring center and just waiting for a public tutor. But if you're below a 40, I would say no, you need to actually cut to the chase. You need to actually make some drastic improvements here, and you're thinking about things very wrong, and you need another human being who can be there in real time correcting your errors. So that being said, let's actually hand this back.